the ones we're going to be interested in are the N-heterocyclic ones. We will come back and talk about the broad family of carbines later on in the class. But, so the families that we are going to be interested in, the first one we met is your imidazolium. These are generally referred to as normal because they were the first ones they became normal. You also can have carbines which are abnormal. And that they bind at the wrong carbon. The more proper term for this is mesoionic. Because you can't draw a resonance structure for this that doesn't put a negative charge on that carbon. You can't have all neutral species around. Usually, the way that you make these is you put another R group on carbon 2 so that you can't metallate there. Because all resonance structures for this have a negative charge on the carbon that's donating, these tend to actually be stronger donors than the C2 carbines. The reason you make these initially is this is a more acidic proton than that one is, so you react with C2 first.
So that nitrogen is positive charge too, right?
Yeah.
Sounds good. So you got two delocalized. Okay, cool. So you got two delocalized charges.
Yep.
Okay.
So there was no way to draw that one that doesn't have charges.
Okay. So because that doesn't have another R group pointing at the out, is it easier for it to dimerize with another?
Yeah, these will dimerize like crazy.
Okay, so
Yeah.
it's easier for it to do.
Yeah, and these are much harder. These are much harder to make.
Okay.
Is there benefit to making?
Absolutely. They're better donors, and sometimes you don't want this geometry. So, actually, the first iteration of Tanai's project was trying to make these. Didn't work. But sometimes you want this kind of a geometry around the other side. Another way to enforce making and buying that normally is to make triazoliums. You don't have a hydrogen on that middle nitrogen of the triazole, you can't bind there, obviously. These are beneficial. They tend to be pretty easy to make. You can make them using click methodology if you want to. Most of the work recently with people doing abnormal binding has actually been on triazoles now. There are other flavors that we'll just kind of briefly introduce. You can have pyridinium, carbines, those are kind of cool. There are also cyclic alkyl amino carbines, which I won't draw because the structure is weird. If you want to know about those, look them up in literature. They go by the lovely abbreviation of CAC. C-A-C. But carbines are really, really useful. They come in all the time. And I mostly wanted to introduce them because when you see them in literature, which you will, you need to know kind of what they are. Because when you first look at the picture, you might assume, oh, this is a metal carbon bond, this is going to be an X-type ligand. These are not, these are L-type ligands. The carbon has a lone pair on it already.
How could we classify these?
Like, I guess what would be the designation, like how many L's, how many F's?
One L.
You said there's one?
One L. Yeah, one lone pair. donating the two electronic.
Okay, so thinking about like what you drew up there, so like will we like experience any resonance that could possibly take place? Or will we treat like any, so we treat like every resonance structure just as like an individual element, or will it shift something in such a way that it could have like multiple cycles?
Changing resonance forms does not change L versus X. Resonance form is our ability to try to estimate what this thing looks like, knowing that none of our pictures are right. Really, it's some combination of all of them. But when we change resonance forms, what we did not change? The bonding structure and where the atoms are. So that's not going to change L. Other questions on carbines before we move on? I bring them in at the phosphine point because they're like a super souped up sigma donor phosphine.
So for triazole,
Yes.
so does the second hand compete with the metal?
No. So this does have a little there, but that is a very, very weakly basic thing. The basicity there is tiny.
When you're making the silver transfer synthesis method, where's the oxygen go? What kind of reaction? What is this? Okay, thank you.
You gotta lose a,
Because I know it, right, yeah, okay, good. And that's why you lose the formal double bond and it goes to that, you know.
yeah, usually there's also a little bit of KOH in here, which helps push this along. In principle, silver oxide is a good enough base to do it itself. So, but often you lose more. Okay. So all of the ligands that we talked about in chapter 4, phosphines, carbonyls, and heterocyclic are all your kind of classic canonical L-type ligands. When you see them in your compounds and you need to do your electron counting, they are L-type. So if you have an L-type ligand on your molecule, you can switch it out for another L-type ligand without changing the oxidation state or without changing the overall electron count, right? So this is a very common reaction. Substitution of L-type ligands. A lot of the synthetic pathways I have drawn up have been substitution reactions. We started with, you have a carbonyl, we put a phosphine on it. We started with a multiple aqua complex and we put a carbonyl or a phosphine on it. Those are substitution reactions. By definition, we've taken one ligand and swapped it out for another one. We did not present them as such, but now we're going to go back and look at these substitutions in a little bit of detail. So let's consider these kind of on a spectrum. On one end of the spectrum, we have what we would consider to be, or what we dub an A mechanism or an associative mechanism. Where you bring in your second ligand, and you form, before you go on and do the substitution, a complex where the metal is bound to both the incoming ligand and the outgoing ligand. In the organic parlance, this is going to be your SN2-like mechanism. You've also got, at the other end of the spectrum, a fully dissociative mechanism, or D. In organic, we would call this SM1. Where first, the metal and its first ligand separate apart. And then you go on and make final complex. There are also, because we're dealing with metals now, and I guess carbon does this too, there is also a whole range of things in the middle, which are collectively referred to as interchange. In interchange type mechanisms, you start to make this bond, and you start to break